Okay, so welcome everyone. Sorry for this short delay. I have some small technical issues here. Uh, I'm glad to be here because last 3 days I spent on a sick leave, so I wasn't sure until yesterday if I will be able to come here, but we are here, so that's nice. Yeah, for sure. I hope that this will make everyone's life easier if you are here. Okay. And today we'll continue with our topic on computer-aided analysis, yeah, of mechanical systems. And about our outline, yeah, as you can see, yeah, we already know a few things from this list, yeah. So we talk about computer-aided analysis of mechanical systems, yeah. So this is not really new to us, which is nice. And we know about multibody systems, how they look like, what is their characteristic, that we are dealing with rigid bodies, yeah. And then we went to kinematic analysis, where the central points are joints, yeah. So we have bodies, of course, yeah. Then we have some coordinate system. We told that it will be a Cartesian formulation. We then connect those bodies using joints, yeah, and thanks to these joints we can perform kinematic analysis, yeah. So this was about formulations of how kinematic analysis looks like. So we needed for this analysis specific joints. Today we'll uh, tell a few more words about this topic, and then we'll go to implementation of the kinematic solver. At least we'll start today, yeah. So we will have a MATLAB session, yeah, and I propose that we will code this solver in sync, yeah. If you agree, yeah, that I will put the part and we will discuss how it should like, yeah, and preferably, if my code works, your also should work, yeah. Of course, then I will upload, I think this time to GitHub, the code that was created today, yeah. Uh, but nevertheless, yeah, I think it could be a good experience, yeah. How do you like this idea? Okay, pretty silent. Let's see how it will work, yeah. But okay, still we have some theoretical part missing, yeah. Fortunately, not too many information are missing. But yeah, so I hope that you remember this slide, yeah, from the last week. Yeah, we were talking about how to transfer the coordinates of the vector from one coordinate system to another, yeah, and there were typically two paths, yeah. So one, it was transfer of the coordinates just of the vector, yeah. So that to transfer coordinates from one reference frame to another reference frame, we are using this. So I already know that it should be, yeah. No, 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 no. Laser pointer, yeah. That we use this rotational transformation matrix to make it happen, yeah. And this transfers coordinates from the vector from one coordinate system to another coordinate system, yeah. And furthermore, then if you want to get a location of this point with one reference frame to another reference frame, we have to also account for translation, relative translation of those coordinate frames, yeah. And then we have this expression that we'll use a lot. Uh, so here is just how the exact what is exact expression for this rotational transformation matrix, yeah. How it's rewritten in the form, and this pretty important information that the reverse that inverse transformation is done just by simply transposing this rotational matrix. Okay, the rest is geometry. Then we are talking about revolute joints, how they're made. I think, yeah, because this is just saying that we get to this point with respect to two different reference frame, so we get this nice expression, yeah, that it's equal to 0. Any questions here? I think it was clear, yeah. Little more questions was about this translational joint, yeah. But I don't know if do you have any kind of concerns about it still. Not really? Okay, great. Yeah. So the first one says that uh, like 2 points on the bodies, or just there is the line, yeah, within each they are moving, yeah. Yeah, so the some points on those two bodies should be on the line, yeah. However, they still can rotate, yeah, because like the second body, we just say that this point P, J, moves along this line, relative line, yeah. But as you will see, this body still can rotate within this point, and still this point will be on this line, yeah. So to make so we need a second equation. So that's why we have it here, yeah. That says that just relative angle of this assembly is constant, yeah. So then we just restrict this rotation, and because we restrict rotation of the bodies with respect to each other, yeah, and then we ask them to move along certain line, yeah, or parallel lines, then we have translational joint, yeah, fully functional translational joint. The rest are technicalities, yeah, how to make those points and those perpendicular vectors or versors. Uh, then we have simple constraints, yeah. Simple constraints are simple, so which is nice, but of course this limits their applicability, yeah. So they are sometimes nice to use if you can use them, yeah. It just makes life often easier, yeah, but they require a little more thought, uh, but yeah, we'll use them, yeah. Then I will ask you to replace for example simple joint with translational joint, but yeah, certain constraints can be simplified when one of the bodies is non-moving. So in practice, it means that in most cases, we apply this simple constraint when we want to restrict some motion of one body with respect to ground. And this is pretty typical because, in all the mechanisms, most of the mechanisms, except when we have some flying or then, but we won't deal with it, are somehow have some joints at the ground. Yeah, so that's why it makes it useful. And for example, here, yeah, here we have the slider tree. Yeah, and according to this image, it can move only in this direction. Yeah, so it can move with respect to ground. Yeah, so how to restrict the motion using simple constraints? Because of course this is just a case for translational joint, yeah, as well. But if you want just to use simple constraints, and they are also typically more efficient and easier to write, you can see that this block can move only along y-axis, yeah. So it means that we can write here two simple constraints in the form that it cannot move along x-axis, yeah. So it will ensure that the coordinate system will stay on the line of the motion, yeah, with respect to y. So x is constant, and also angle of this body is constant, so it won't rotate, yeah. So we can replace this translational joint for those two simple joints. Make sense? Same applies to the second body, yeah, number 4. Here we it moves in the axis that is parallel to x, yeah. So it means that its coordinate, if you have system here, yeah, uh, its its y coordinate is constant, yeah, because if you move here, the y is always the same, yeah, thanks to the geometry. And the same, we can constrain angle, and we'll get two constraints that works. Okay, so this is the basic idea. And here are just this type of I just want to open this movie to see if there's some comments. Not really good. Sorry for this break, but so here are just general expressions. Yeah. So simply we are constraining one of the coordinates to be constant to use this functionality. Yeah. And here is shown just example that we can constrain in x coordinate. So then it means that it is moving along y. So here are yeah expressions. Yeah. So simply we are constraining. So now I have to mute it. Perfect. Here is y constraint, so it's moving around x. And as you can see, if we just constrain one, it can also rotate. Yeah, because rotation doesn't change the location of the system, so it will still work. And here, if we constrain just angle, yeah, it can move, but it has to just keep orientation. So it can move within our plane whenever it wants, but it has to keep the orientation. But we'll use it mostly in the way that are shown on the previous slide. Yeah, that for example, if something is moving along some axis here, then we can just apply just two of them. Yeah, just like was shown. Is it clear? Okay. So if example was clear, that's great. Now driving bodies. Yeah. So we will use one of the main reasons why we talk about the simple constraint is to apply driving constraints to drive our joints. Okay? Uh, you can, of course, add this kind of driving constraints to any type of the joint, but this is the easiest to be done using the simple constraint. Yeah, once again, formulation is pretty simple, so it's also easy to add. Yeah, when you have more complex joint and you want to add very general way, it requires some effort. Yeah? And for our use cases, and for many practical use cases, this is more than enough. So, what are driving bodies? Is it clear what are driving bodies and how it fits into context of kinematic analysis? So first of all, why we need driving bodies in the context of kinematic analysis? Yeah, so in the kinematic analysis, we are analyzing the motion of the system, but we do not consider forces. Yeah, and to analyze it properly, the motion has to be defined uniquely. Yeah, so let's say that we have this kind of slider crank mechanism. Yeah, it has 1 degree of freedom. Yeah, so it means that it has some freedom to move the way it wants, yeah, in the one way only, but still. So and simply, if we do not consider the forces, so we do not want to generate equations of motion, we have to constrain this only available degree of freedom, yeah, because we want to analyze the motion. 1 degree of freedom is free, so one way of moving is free. And to analyze it in kinematics, we have to define how it moves. Okay. So, and we are doing this by using those driving concept of driving bodies. Yeah. So like here, we would tell that this link will rotate, for example, with constant angular velocity omega. Yeah. So this defines how it moves, yeah. And with this definition, like in your home assignment, yeah, you can tell how moves the whole system because you define the only free way of moving, yeah. And technical way to do this is by using driving bodies, okay. Uh, and here it's just written how it works, yeah. So for this case, we would say just the angle. If we have, for example, some coordinate system here, yeah, and we have some angle, we'll tell that the angle will change with time. And this is the description. So, for example, here it rotates in positive direction, so it will be omega t times this phi 0, yeah, because we have to account for 0 angle. Well, it's written here, exactly. Yeah. Yeah. And that's all of the philosophy here, yeah. And it's worth noting that while standard joints constraints depends only on coordinates, yeah, so that doesn't typically depend explicitly on time. Yeah, here those constraints depends explicitly on time. Okay. Questions, doubts? Make sense? Perfect. So with all that, so if we define our system, our bodies, and we write our constraints, and we add those driving constraints, then we have full rank system. Yeah. So for example, we have system with like the slider crank. It has 9 coordinates. We can define 8 joint equations based or constraint equations based on the joint in the system, and we can add this one driving constraint. So we have 9 coordinates, 9 constraints. System is fully described. It has full rank. We can solve it. Yeah, and then use, for example, Newton-Raphson. So yeah, so constraints are in general nonlinear with respect to Q. We have seen it. We have seen those sines and cosines in our systems. Yeah, and number of the coordinates describing the configuration. So this is the length of the vector Q. Yeah, how many coordinates do we have? And number of kinematic constraints, CQ equal to 0. Yeah. Yeah, so those are kinematic constraints. In the case of the slider crank, it was 8 because we have 4 joints, yeah, for those 3 bodies. K is number of system degrees of freedom. We need K driving constraints to solve the system. We already told why, because in kinematics, we describe the motion without forces, so we have to define this motion. Those equations can be used to obtain unknown Q for given t, time t, yeah? Similar to your home assignment. And here is procedure, yeah? Position analysis. It's simply to solve C equal to 0 using Newton-Raphson method. Make sense? Yeah. Velocity analysis has to be, first you need position analysis to perform velocity analysis. As you can see here, we have Jacobian. Here we have our velocities, because as we have seen, they when we differentiate it, they depend linearly. In practice, this equation is C dot equal to 0, just rewritten in this form. And here on the right hand side, we have the time dependence. Yeah. And here are just those joint equations. And here is for acceleration analysis, because this is C double dot equal to 0, it's slightly more, okay, it looks pretty complicated, yeah, but don't bother with it. Yeah, we will not use, as it's written here, we will not use those equations directly. You can, of course, yeah, if you want, and if you want to make some checking, but there is typically no need for it. Questions? Here I would just want to know that we have in general those 3 types of analysis, because we are interested in the positions and next in the velocity, and at the end with the acceleration. Yeah, typically we will stop there. And to understand that to solve for position, we have to solve nonlinear equation C equal to 0 for given t and q0. Yeah, and then we will get q of our configuration. And then to perform velocity analysis and acceleration analysis, we have this kind of similar equation. We have Jacobian times our unknowns and some things that we can compute on the right-hand side based on our joints. And those are linear systems that are just solved in one line, yeah, using this ML diff in MATLAB. And the same applies to acceleration analysis, Jacobian, accelerations, and some vector on the right. We'll call it, for example, G or gamma. Yeah? Okay, makes sense? Nonlinear, linear, linear. We could, in practice, start even implementing the stuff, yeah, or we can get to this position vector derivatives. Any preferences? Should we go through this story? Okay, maybe we can go. Position vector derivatives. Yeah. So why it's here? Because again, we need those derivatives. Yeah. Because for example, as you remember, this equation take part, for example, this in this revolute joint. Yeah, so we have it once minus second form. Yeah, and we know that of course, this is required for position analysis, but then if you want to get to velocity analysis or acceleration analysis, we need time derivatives of all these vectors. Yeah. So here we are to time derivative it, to calculate derivative of it, to use it for our analysis on other levels. It will be also very useful for, it's also, all those parts are also needed for dynamic analysis. Yeah, so reuse all this code. So, okay, so let's go differentiate it. Yeah, so here it's written because it's pretty simple. Yeah. We know that, I hope that you remember that this vector is constant, yeah, typically. We have rigid bodies, so it's constant because it points to the certain point in our bodies. So this depends on the coordinates. And as you remember, it's this kind of this was this rotational matrix, and it has this hidden cosines and sines of angle theta. Yeah? And this just depends on the location of our coordinate system. Yeah. So if we have for our body, we attach coordinate system and have coordinates x, y, and phi. Yeah. Here we have x, y, and here we have phi. Yeah. So simply, if we time derivative this part, we have time derivative of this, and this is just velocity of how, what is the velocity of our reference frame. Then time derivative of this, because it depends on angle, and that's all. Yeah, because this is constant. Yeah. So this stays like it stays, and here just appears omega and theta prime to make it work. Why? Simply because AI contains just sines and cosines. Yeah. So for example, time derivative of sine phi, yeah, is just cosine phi dot, yeah, and cosine is minus sine phi times phi dot, yeah. So all those terms contains phi dot, so it appears here, and because still cosine to sine to cosine, yeah, they just change the order and sign, yeah. So simply with this omega transformation matrix times A, we get what we need. Yeah. So simply time derivative of this matrix A with respect to angle, yeah, it's simply omega A. Questions, doubts? Okay. Second derivative. Same in principle, yeah. So here we have our original equation. So r double dot for the first term, closed case, yeah. Here now we have two things that we can differentiate, that one and that one. So so here we differentiate the second one, so simply double dot, yeah. And here we differentiate that one, so we get omega omega a and this squared, and simply omega omega is minus identity matrix. You can check it with just a few lines of calculation. So that's why we have minus a s, and this is squared because it appears. Clear? Easy to follow? Perfect. And this is what it is. Okay. So we will just then use this in code as granted. And this is now what we want to analyze. Yeah. So we want to analyze this slider crank mechanism. Yeah. So 3 bodies, 4 joints. Yeah. So 3 revolute joints and 1 translational all simple joint. Yeah, or 2 simple joints. Here we have dimensions, locations. We have to locate somewhere our reference frame. We can use those points, this point G. Yeah. And here we put it, we can put it wherever for kinematic analysis. Yeah, typically, you know, at least I'm used to put it, if no other reasons, in the middle. So let's put it in the middle. Yeah, and here at point A. Here you can see just numbering of the bodies. Yeah, so here we assume that the body 1 is simply ground. Yeah, so we have body 2, 3, and 4. Yeah, this is customary. We can apply, use this way. Yeah, because we can either get rid of the ground and write special version of the joint. So if ground, do this, if not ground, do that. Yeah, or we can just assume that we have ground, and we constrain ground using simple constraints, that in the way that, you know, it cannot move or rotate. So we just fix it. And then equation for constraints are just slightly simpler. Yeah, because always there is somebody. Yeah? So because we have just here numbering 1, 2, 3, and 4, we'll follow this approach. So we'll add the ground and then simple constraints and follow along. Okay, here we have defined where are locations of our local coordinate frames. So we'll follow it for consistency. And here is the full assembly. Any questions to this example? Just example. Yeah, makes sense? Looks okay? Perfect. So now it's time to run MATLAB. Okay. So here I have just empty MATLAB session, and we'll code everything there that we needed. Of course, we can have two approaches, top to bottom or bottom to top. But I will start with defining what do we want, and then we'll just implement all the features on the go. Yeah. Let's see how far we will go with today coding session, and how we will shape our program. Yeah. We'll try to use some reasonable programming principles. Yeah. So you don't have to follow all of them. It would be nice. Yeah. I wonder if, do you think that we should write tests for our code? Do you want to see how to write tests? Yeah, I know, but you know, one in programming is close to zero. Yeah, one is really close to zero. Yeah, so it's yeah. So and in programming, it's almost only about practicing. Yeah. So so okay. So let's give you a minute or two for just setting things up. Yeah. As I told, everything that I will write here, I will upload for you on GitHub. So then you can just download it. Yeah. Why on GitHub? Because when you okay, do you know why on GitHub? Okay, so first of all, why not on GitHub? But do you know what is GitHub? No, not really. Okay, so maybe let's. So maybe I will just log out to see to get to the this page. Yeah. So is it written here? Okay, I think that you know, it's just company web page, so you will get the more information about GitHub on Wiki. So if you don't know GitHub, it means, for example, that you are not professional programmers, because it would be strange if you are professional programmers and you don't know GitHub. But because this is the tool used for professional programmers, I think that it's also very good for you to know it. Yeah, maybe you can. Okay. So let's start. What is GitHub? So first of all, this is, of course, this is commercial service, yeah. But this is commercial service that provides you version control system using Git. And why I talk about this specific one, because this is the most widely used version control provider on Earth. There are others, so we can use others, yeah. But okay, do you know what is version control system? Version control system in software. Can you see this? Maybe I can, make it larger. Yeah. So yeah, it's the concept from software engineering, but it's useful for everything that you can do that is preferably text-based. Yeah. So even if you write some things, especially in Markdown or LaTeX, yeah, then it's very also nice to keep the version there. Version control, revisions, source control, code management. Yeah, it's a class of system responsible for managing changes to computer programs, documents, large websites, or other collections of information. Version control is a component of software configuration manager. Okay, what is important here? Managing changes to computer programs and other stuff. Yeah. So it keeps your source code or your document code or your website or whatever. Yeah. And then you apply there your changes in batches. Yeah. So for example, today we will work on create a body. Yeah. So then we can add this. So then we are adding some functionality. We'll test this functionality. Then we can create so-called commit and commit it to version control system to keep it in sync. Yeah. So it is the way to keep your software, and this is the way to keep the whole history of your software. Yeah. So you keep there your source code, information about who makes changes, what kind of changes was made, when it was made, and all sort of information. Yeah. This is the tool that makes it possible, for example, to keep different versions of whatever software available. Yeah, because then you can also create branches and other stuff, so you can really make this kind of code management. We won't dig into it because it's too complicated. For us, it's important that it keeps the version of your code and keeps the history of your code. And can be pretty important, yeah, because simply bad things can happen, yeah. For example, you can just lose your code, and sometimes you can even make it changes to the code, and for example, it stopped working, and you don't know what you have done, because it really, when I joined this university and this lab, sure after, yeah, it was the case that one of our PhD students, written his code, yeah, and get some results for a paper. Everything works nice, yeah. But then he makes some changes, yeah. And the issue with these changes is that typically you make few changes, yeah. So he makes changes here, there, and so, yeah. And bam, yeah, it stopped working. And it takes like month or 2 months to get it back to the state when it works, yeah. So really a big loss, yeah. And with source control, you just revert your commit, or you just pull different version of the software. It will take a minute. Or another case was even earlier, that simply the code get lost, yeah. So one PhD student was working on the code, and then yeah, but he said, but now I don't know where it is, yeah. Not very nice experience, yeah. And then you have to recreate all that stuff, yeah. So if you are anyhow serious into programming, you should learn Git and GitHub. Then you can go to other if you prefer, but this is some kind of gold standard, yeah. By the way, Git was created by Linux creator Linus Torvalds, yeah. I'm not sure if my pronunciation is correct, yeah. And here he's from Finland, so sorry about that. But he created to manage code for the Linux kernel. Yeah, and you can imagine code for the Linux kernel is pretty challenging to manage because it's just massive. Yeah, and just thousands of programmers works there. Yeah, but okay. So, but it works also very well, and I use it also even when I do stuff by myself. Because simply, it's very useful to have this kind of history. It's not very, you don't need this feature all the time, but when you need it, it's just great to have it. So, because of the nature of our code here, because we'll write this in batches, yeah, uh, you will simply see the history of the code on the GitHub. You will be able to download it. So today we'll write a part of it. Next time we'll write another part of it, and all the parts will be there. So there will be always actual version there. Yeah. If you are interested, because this is very popular system, there's plenty of the resources about use of the Git. Yeah, so some Git cheat sheets, yeah, or just some information of how to set it up, plenty of information. So yeah, but still, if you want to know something, I can share some things with you if needed. Yeah, it's available on many systems, yeah, and if you are using Windows, simply if you are still on this topic, yeah. So first of all, it's Git for Windows. So here is if you want to just to download and start using it. So this is the tool, yeah. And preferably, it's good to know a few comments about Git. In programming, command line is indispensable. Like here is almost the form of the command line. And yeah, let's say if this, okay, a little wordy, too long maybe, but you can always ask ChatGPT, for example. I'm sure that it also will answer your questions well. Because here, of course, they start from you to know, understand everything, and it's not really needed. I mean, maybe I will share one link. I remember that I found a web page that shows this in a pretty nice and straightforward way. But yeah, but this is about Git and GitHub. Any questions? It is more or less understandable why to use it, this software, and why it is useful. Okay, let's get back to those fonts because they are again too small. Okay, so about our code, yeah. So where should we start? Uh, we'll start with top, yeah. So I will first recreate a script. Uh, and I will call it just slider crank example, or maybe kinematic analysis. I think slider crank kinematic analysis to say, simply what we are aiming to do. And this will be script file, yeah. So this is the script file, and firstly, you can skip if you want, you can skip those comments. You will be able to find them later here, but I will write that what we want to do. File is quite descriptive, but we want to just perform. Okay, so kinematic analysis of two-dimensional, so maybe just planar slider car mechanics using the multibody formulation. Okay, the design goes to implement the software as a general solver. Yeah, do you know what does it mean, general solver? So okay, so as it's written here, we want to have this kind of general solver, yeah, and we'll use it to analyze only this mechanism, and your task will be to use to analyze some other stuff, yeah, and to also to add some missing features, yeah, along the way. Okay, any questions? So I think that here I should have also some extra slide, yeah, about what do we need. And so this is our example. Yeah, we already discussed about this, and here it's written what do we need to solve it. Yeah, so maybe the order is not the best because firstly we need some coordinates and constraints, but it depends. Yeah, because we want to solve C of Q equal to something, and we want to get this Q. Yeah, so let's focus now on position analysis. So we need constraints, and for this analysis, we need at least constraints for revolute joint and simple joints. And also we need driving constraint. Is it clear? Yeah, because we need revolute joints for those joints. Yeah, we need simple joints to put the ground as a ground to fix it. And also for example, we can define the motion of the slider using simple joints. So that's why we need simple joints. And to, again, make kinematic analysis, make the system full rank, we need to define this motion, this rotation of the crank by using some driving constraints. Newtonian Raphson solver, we'll copy it. We already have it. Yeah. In practice, we don't even need it. Yeah. In theory, as written here, we can just have constraints, coordinates, and then we can use fsolve. Yeah, you know fsolve? There is one function that can be used for solving nonlinear equations. Yeah, it's very robust, like many codes in MATLAB, but it's also very slow. Yeah, so that's why we can use it just, for example, as reference, because it's always good to have some reference, and then we repeat the solution using Newton-Raphson that we have written. We can then even analyze how faster or slower is one solution with respect to another. Okay, makes sense? Okay, so to-do list. Yeah. So here I will put some simple to-do list. So coordinates. We have to define our coordinates. What did we have here? Yeah. So we will start with simple constraints because we need it, for example, for the ground. Then we need revolute. To-do list to implement our example and solve kinematic analysis on position level. Yeah. So because then if we want to go for velocity level, we have to add some more stuff, and acceleration the same. Yeah. And then it was driving constraints. Test call to fsolve, just to see if everything works. And next, it will be Newton-Raphson. Okay, so maybe it should be enough for today. Uh, is it clear? Do you have any idea how to start? Because now we start to have, this kind of a little challenge, how to design our software. And this is difficult task to answer, yeah? So, because here the software is not super critical in any way, so we won't use any strict methodology. But okay, still we have to make some decisions, yeah? Design choices implemented. And especially with the source control, if we change our minds and we decide that some decision that we have made is just incorrect, if we are using version control and tests, then change of design is much easier than in other cases. Simply because, first of all, source controls gives us previous version if we will fail, because then we can just experiment. You can experiment. Okay, yeah, I have idea that this will, make it 1,000 times faster. Yeah, but then you code it and it's 10 times slower because you haven't, thought about one stuff. So then you just revert it, discard it, and just forget it. So this is also nice. Version control is now very nice for experimentation. And why test helps here? Because tests keeps your code on the working stage. Yeah. So if you run the test, you know that all those small parts are working. Yeah. So if you code something, change something, okay, and you then run code test, okay, it's broke. Compatibility with other parts. Yeah. But then you know what is broken. You can get just to the things that are broken. Yeah. Fix the things that are broken or fix your tests. And then if test runs, you have good chance that your code is also good to go. Of course, tests are not bulletproof. They are just the safety net, yeah. But if you put too much pressure on them or just use some strange cases, then get out of this net. Still, you can get some errors, yeah. And but again, it is to minimizing this risk. And if you discover that your test doesn't consider some specific case, you can always add new test. Okay, makes sense? Yeah. So also, I think that in most professional programming environments use at minimum those two tools. Yeah, so tests and GitHub, plus also a lot of automation tools. Yeah, but we won't get into automation because we don't have time for it. So this is about the part why we are going to do the way we are going to do. Another part is now just to fill this list. Yeah. So first stuff is on the list is coordinates. Yeah. And coordinates are attached to bodies. Yeah. So the simple way is to just add bodies. Yeah. And have those bodies property like coordinates. Okay. And then we have to keep the list of those bodies, because we have to keep it somehow in memory for our reference. Yeah, makes sense? So, mm, so I propose that simply, so simply to have coordinate, because we need our bodies in either way, yeah. And now it's just a question, where do we keep our coordinates? This question is not so trivial, like everything, yeah, because we want to have our coordinates to be stored in vector Q, yeah. And we have to find a way to store initial values of our coordinates, and then we will update those coordinates. However, we need also to know which coordinates belongs to which body, yeah, because then when we have those equations, then we have to reference to it, yeah. So one simple approach, let's see if it will work. If it won't work, we'll go back, yeah, and implement it, yeah, is to have a structure with bodies. So simply, yeah, let's start with the ground. Do you know struct from MATLAB? Not really? No? Okay. So let's start with defining one struct, yeah. So okay, so at least it works. So this is example of our body. And as I understand, you don't know, you are not sure what I have written here. Yeah, so, and we will use structs here extensively. So what are structs? Yeah, as the name suggests, somehow those are structures. Yeah. So in simple words, you can have different types of data types. Yeah. So this is one version of data type. Yeah. And as I suppose that you know those basic data types in MATLAB, yeah, or in many other programming languages like string, like this simply float, that it's some kind of, or doubles, it's just number, or arrays, yeah. Structures just combines many types of those data together, yeah. Uh, why? Simply because, like here, we want to have many things grouped together, yeah. Like here we want to keep the information about some indices in our body. We want to have to keep information about where the body is located. We can even keep and I think it's a good idea to keep the name of the body, yeah. So we will even keep a name of the body, yeah. So and in very simple words, struct is the tool, this data format that can allow you to keep all this information together. Make sense? So let's go to maybe uh, structure array. Yeah, it's called in MATLAB. Uh, okay, yeah. So if you don't know it, I think that it would be a good idea to go through help for it. But simply, it's the data type that groups related data using data containers called fields. Okay, so fields are those stuff that we put here with the names. Yeah, so a structure with fields. Yeah, I have changed it, so call it once again. Yeah, so this structure has three fields: name, index, and q0, and it's of type string and some vectors. Yeah. Each field can contain any type of data. Okay, so it means that we can really group different type of data like we have done here. So we group string information together with some numerical data. Access data in the field using that notation of the form struct name, field name. Yeah. So if we have this ground, yeah, ground name is ground. Yeah, this number. Yeah. And here is the ways to create it. So there are many ways. Yeah, here we can see one way to create it. Another way to create it is to start with that. Yeah, so define that ground. I could put here that ground that name is that one, but I just use it because I just want to put all this in one line. Yeah. Syntax, I use this syntax: field name, value, and you can repeat it for many times. This is just empty struct. Uh, And that's all do we need. Yeah, we'll just use it to create group our things together. Yeah, so we'll have array of structs for our bodies, and then we'll have array of structs for our revolved joints, for our simple constraints, for our driving constraints, and then we'll have I propose that we'll keep all this in one top structure that will keep the information of the whole system. Make sense? So then you have just one variable that holds all the information. So if you want to calculate something, you just have to pass this one variable. But then using those dots, you can get into this variable to all the fields. Okay, make sense? Any questions? Okay. So, but we will, okay, so here now we create this struct with the three fields. And to create, then we can create the next one for example, crank, link, slider. Yeah. And then put them together in one array that can be called, for example, bodies. Yeah. Uh, and we will do this. But before we'll do this, we'll write our first function. And the first function will be to make this structure. Okay. So of course we can copy paste this line of code. Yeah. And then just put here other names, indices, and Q0 values. It's totally doable. Yeah. But we don't want to do this. At least I don't want to do this. Yeah. Do you know why I don't want to do this? Yeah. Yeah. Okay. So this is one good reason. Yeah. Because then it just can be done in more compact way. Because either we have to provide all those fields, yeah, but there's another reasons as well. So yeah, this is true. Another reason that I want to do is deals simply with programming. That simply this code is error prone if we do this that way. Yeah, because we have to keep in mind that those names indices are Q0 to use exactly the same field names. Because if you make an error in this field name, it won't work. Yeah, we all. So this is one reason. Another reason is just aiming for abstraction that, it's done something, but we can change the names of those fields or types of those fields or use of those fields if we need. And it shouldn't be exposed to the user of API. Yeah. So if you just make body ground and, this is all he should care about, and all the rest should be, taken care inside. Uh, and also we can validate it. Yeah. So for example, we can tell the user that because here there is nothing to put here some kind of the enormous input, yeah, and it will still accept because it will accept all the things, yeah. And simply by using function, we can validated. Yeah. So this is what I want to have. Yeah, but I would like to have it in the way uh, how to call the function make body. Is it a good name? Add body, create body. Any ideas? Any preferences? Okay, so simply go with add body. So I would like to have it in that way. Is it enough information to make a body? So now it depends. Because here we have zero coordinates, so we can assume that zero coordinates are default because it's typically good default. Yeah. So we can either put explicitly coordinates here or just skip them. And what about indices? I don't think that we should at all put them because of two reasons. Yeah. So at least two reasons. Yeah. One reason is that once again, it's implementation detail. Yeah, maybe now we use indices. Next time we'll use something else. Yeah, because we can just put this just like single index and have it somewhere else. Yeah, but this is a little abstract. But what is more important, we have to have those indices consistent. Yeah, so we have to have it for first body 1, 2, 3, for the second body, for example, 4, 5, 6, and so and so. Yeah. So, and it's not a good thing to tell the user, just remember about not only adding bodies, but remember also to keep this number in group of three, and that they are consecutive. Because this also asks you for the error. And also, this is not very nice for use for the user because let's say that you have huge mechanics that has 10 bodies, yeah, but then you thought that okay, this the second body is not needed because of whatever, yeah, you change the design, yeah, and then if you remove second body, then you have to also change indices in body 3, 4, 5 up to 10, yeah, and this is not very user friendly, yeah. So while of course we need to provide some information about coordinates in general, because like here on this slide, you know, each body has different coordinates. Yeah. uh, but you know, this indices should be taken care internally. Any ideas how to do this? Okay, so I have one proposal. So we will start not with adding bodies, but we will start with creating a system. Okay. And the idea is that if you create a system, then you can add body. So so what I would like to do, yeah. So I would like to get step back, yeah. Okay. So first I would like to have some, for example, sys equal to something like that. So make system, yeah. And then this is the information that we want to hold there. And then add body to the system. Okay. And what will be the system? System for our will be at start will be something like that. Yeah. So system is a structure that holds, for example, bodies, and then we add body to our system. Okay. And how it help us? It helps us in very simple way that I think it must be struct, empty struct. We can test it later. What has to be written here? Yeah. So let's don't bother. It's just mostly about the idea of how to make things happen. Yeah. While why it will work? Yeah. So it can work in the way that simply you will see we have no bodies. So it means that, we have to start indexing from one, from the start, yeah? So the first body will be assigned indexes 1 to 3 automatically. Don't have to bother with it, yeah? Then when we add another body to the system, already we have one body. We know that the index of this last body is 3, so now we have to go further, yeah? So then we can very easily, by holding bodies here, and we still have to hold them somewhere, yeah? But holding bodies here, uh, when we add those bodies, we can make this kind of processing internally. Not to bother user, make it as internal implementation detail, and yeah, and to make the code safer to use. Okay. So we talk a lot about this. Now we need to start implementing stuff. Yeah, because now when we try to run it, of course, we get very quickly to the error, unrecognized function or variable make system. Yeah. Do you have any questions about why we are doing things that way? Is it clear? What are my goals? Okay, so let's make a new file or just home new function. Let's make a new function. Make system because this is the function that we need. Uh, at the moment, let's see if we'll change it. Our function takes no arguments and it returns simply just system definition. Yeah. So what is the role of this function? Yeah, so create empty. We'll make many changes to this file because now it holds only bodies, but then it will of course hold our constraints and possibly many other stuff. Yeah, but just to start with something, we'll just take this and put it here. Yeah. Sorry. So now when we simply this of course doesn't work because we still don't have this function add body. When we just run it, we just get here. Okay, maybe I will just clear the stuff. So maybe I will just put this clear here to make sure that our run is done properly. So we have this kind of sys, and it has just bodies, empty bodies, yeah, because this is what we are expecting. We are aiming to hold here bodies, yeah. And now we already can write a test for it. Can we write a test for it? Of course we can. We have function. We can write test for it. What do we expect for this function to do? Yeah. So yeah. So we can express this in the form of tests. Yeah. So we can create a new script and we'll call it why it's not collaborating with me. Okay, I don't know why it doesn't want to work with me, but okay. We'll call it test make system. Uh, and we'll just write this simple approach for testing. So we'll just write those testing using cells. Yeah. And the first test, we'll just tell us does system store bodies. Yeah. So we'll just call it sys equal to make system. And then assert. Okay, so now you have to know a little about the struct, but we can just ask is field sys by this, then is message. I think that it won't work that way because we use strings and let's just use it as a function. Uh, so will it work or won't it work? Yeah. Okay, so it doesn't like to mix this, so why it doesn't like it? Okay, now it's better. So this is a very simple test, but on the other hand, it must be there, yeah. So nobody tells that the tests must be super sophisticated, yeah. Sometimes, when we create something like that, we just expect to have it there. And another thing that it tests that it runs without the error, and it's not so trivial because it can easily make some changes and it starts throwing errors when you create empty system. So yeah, this is useful test if you have large code base and start playing with the code. So let's run it. Well, one passed, zero failed. Okay, nice. Uh, then I will add another test. Yeah. That we can write test that we are expecting that there is nothing there. Yeah, that we do not create a system, empty system, and we have some bodies already there because of whatever reason. Yeah. Okay, so Yeah, so just like that, and then warning that the bodies of the newly created system are not empty. So it's saved. Oh, no, I don't want to run it. Okay, works. Sorry, I just press something. Yeah. Okay, as you can see, I ran those tests and two passed. So it's okay. Yeah. So we are good to go. Yeah. Do you see the reason to write this kind of tests? They ensures quite many things, yeah, and especially if you play with it. But okay. So get back here, yeah. So we update our to-do list to see that something was done, yeah. So create an empty system. This is done. And so the next stage to get coordinates will be add bodies, yeah. And then after add bodies, it will be get coordinates. Okay. So we know we now want to add body to our system, yeah, and so we need to write this function. So what is the shortcut for new function? Okay, no shortcut for new function. Add body, yeah. And this is also pretty interesting concept of what to put here and what to return, okay? Because what to put here is pretty easy, yeah? So we want to put here as system, yeah, to because we want to add body to the system, yeah. And the second argument we already decide its name, okay. And the third argument are initial coordinates, okay. So let's say that we'll use this type, but what we should return from this function? Should we return something from this function? Yeah, your intuition is right, but not really in MATLAB. You could also, yeah, but this is a little specific to MATLAB that we have to at least return sys. Okay. Why? Uh, Maybe you remember that we discussed about the thing that in MATLAB arguments are passed by copy. So if you make changes to argument, they are not expressed outside. Yeah. So if you would add body and do anything to the system, then it won't be seen outside. So to see it outside, you have to return system and reassign it. Okay? So this is the way you must do in MATLAB. Yeah? In other programming languages that rather go through reference, like in Python, Julia, and many others, yeah. In C++, you pass by copy, but you can use pointers or references. Then you could pass here things that you can change, yeah, and then it would solve the issue. But here you cannot do it in easy way. It's possible, but we don't want to get there. So in general, we have to return the system. We can also return body, but yeah, we can also return body. Yeah, but it depends on our design choices. Let's just return system to keep it simple. Okay. So it means that here we rather, or do you want to return body as well? Because we need to return system because we cannot go over it. Yeah. So let's say that we return the system, and system will contain body, and then we can find the body by using its name, for example. Yeah. Agree? Okay. So we plan to use this. Now is the question, if do you want to use this approach here, that missing values of the coordinates are assumed to be zero. Another thing, that if you want to provide here a vector, okay, because let's say the name, will stick with the name, yeah, but do you want to provide it as a vector, or if you do you want to provide it as separate coordinate, x, y, and theta? Those are all the valid choices, yeah. And we have to make some decision. So how do you prefer to proceed? Do you want to provide this as separate three numbers by comma, or do you prefer to provide array because you want to define it area or whatever? We don't have to even remember it. We could provide a structure for it. But yeah, that's true that in MATLAB it's hard, because in other languages, okay, you can pass values by using names. But okay, yeah, do not overcomplicate it. Yeah. So okay, we'll follow as you said. So we'll just provide an array and of x, y, and theta. We won't, because we have coordinates. You can already make a structure, but yeah, we have to at some place cut it between usability and readability. Okay, so we'll follow this. Yeah. And initial coordinates. So so initial coordinates holds the value of the x, y, and theta coordinates. Just to have it somewhere. Is it okay that missing values of the coordinates are assumed to be zero? Or you don't want to use this assumption? It's okay? Okay. So how to add body? Yeah. So first of all, we have to create a body. Or we can just use this, maybe it's even simpler, yeah? Body name equal to name. Okay, nothing crazy. But should we use initial coordinates or Q0? Okay. Our initial coordinates, yeah. And now we have a third one that we already told we can foresee that it will be useful. Do you can foresee that it's super useful to have indices? We need them in one way or another. Yeah, for example, we need them to make values, put values into Q. Yeah, because we have to this Q and we want to put values there, of course. Yeah, so we have to store it somehow. Yeah, so if you found some spelling error, just let me know. Yeah. And now it's a good question how to make it, because we know that for our body it will be 1 tree. But of course, it cannot be 1 tree for all the bodies, yeah? It's for only for the first body. So how to know where to put here exactly? There are of course many ways to do this, yeah? Uh, we can either reference check if the body is empty. If it's empty, then do this and that, or we can just make it even simpler, yeah, and we can add to our system number of coordinates. Do you want to add here number of coordinates or not? Do you think it will make our life easier? Because we can just calculate number of coordinates based on the, but we can also write a function number of coordinates. What do you prefer? Use a function. Okay. And then we can, okay, it's very good choice because even if you have coordinate number of coordinates, even if we have here field number of coordinates, we can use it or not. And then we can decide what is better for us, yeah? So we can write a function. Uh, Number of coordinates. Is it a good name? Or system coordinates? Number of coordinates is a good name? Function n, number of coordinates. Sorry, and it must work for system because this makes sense only for the system. Yeah, that you want to know how many coordinates do we have in the system. Yeah. And then we need this kind of okay. Yeah, it's pretty trivial. Yeah, and n is in our case equal. What is n? So what it should return? Yeah, so 3 times, very good. And what is number of bodies? Should we have function number of bodies? Okay, maybe if we don't explicitly need it, let's go. So, but how to get number of bodies? Yeah, but it's just length of cis bodies. Will it work? Maybe it will work, but we should write test for it. So now we need a new script. I don't understand why it's not working. I will just do this to get the proper name, yeah, because I want to call it test number of coordinates, and somehow this pasting text to this field doesn't work for me. Okay, and the first test will be answer to this question, yeah. So if we have sys to make system, and also you can see that, you know, having those functions make writing tests easier, because if you have this function as a struct, copy paste somewhere, yeah, it's a big mess, yeah. And then we know nc equal to number of coordinates for our system, and simply here we want to nc equal to 0, yeah. Mm. Of course, it's not. I don't know how to write it in this form, so I won't pretend that we can use functions as humans. And now we of course should run test. And okay, at least it works for empty coordinates. If it works for more, we cannot test. When we have the function to add bodies, then we can ask if we add 2 or 3 bodies, it works properly. And now we cannot, because we don't have a good function for adding bodies. Yeah. But now we can get back to our bodies, and here we can write simply something like that. Yeah. Now we are in function add body. I don't know. I don't know if I can change this. Yeah. But okay, here we have the name of the function, so it's not so bad. Okay. Okay. So now we have initial coordinates are initial coordinates. Coordinate indices, number of coordinates of the system plus 1 to 3. Okay. It should work as expected, hopefully. And now we just have to attach this body to our system. Yeah. So, well, it's nothing fancy. Yeah. So sys bodies equal to sys bodies and body. There is no room to being too fancy here, and that's all. Yeah. And now it should work. We attach body to our list of our bodies. And now it should work. Or not, depending on many stuff. Yeah. So let's write a test. So now okay, at least that way I can paste it. Test add body. Okay, and here we would like to I will check something. Okay, we have something like that, which is nice. Okay, it's pretty new. Okay, because what I want to do, I want to do that one, yeah? So I would like that when I add body to the system, it doesn't throw exception. So just I want to check if it works, yeah? Because this is the most important, okay, there are many important things, but this is the most basic stuff. It must first work, yeah? And then we can check if it works properly, yeah? So, and typically the test should be simple. So, okay, by the way, what do we have here? Assert. Not that one. Okay, never mind. Assert success. So add body ground. And of course we have to provide system, yeah. So should it work? Mm, no, it shouldn't. But do you know what I want to test here? Is it clear? Yeah, it it shouldn't. Of course, it should work. We want to make it work, but this won't work. One fails. Yeah, and then with the test framework, you can see that what fails, of course, does adding body ground to a new system work? Fail. Why it fail? Okay, I know it fails simply because we haven't implemented exactly in the way that we wanted. We haven't included this part. Missing values of the coordinates are assumed to be 0. Yeah, this part is missing here. So it fails because initial coordinates are not provided, and there's nothing here that make it happen. So we have to include this. But can we do this after short break? So can we have like 5 to 10 minutes break? Is five minutes enough or okay? So just because now we are sitting and coding a lot, but yeah. So let's have a short break, and after the break we will fix this, and that's all. We'll fix this, and then go with getting coordinates from the system and adding some simple constraints. Okay. So now let's have a break. So I put here a break. And yeah, see you in 5 minutes. Okay, so we are getting back online and we want to make this working. So do you know how to make it working? In MATLAB? MATLAB doesn't support, as far as I know, default arguments. We can check it this online again, yeah. But as far as I know, it's not the case for MATLAB, yeah. But we can never be sure because, of course, they are developing it. So, uh, how to support default parameter in MATLAB function? So this is something that we want to know, yeah. As I know, there is no default parameter support in MATLAB. It's pretty fresh. So at least one answer is pretty fresh. So let's see. It's the methodology through which it can be done. MATLAB is an interpreted language, not a compiled language, so there is no compiler as such. Okay. In any case, there is no inbuilt syntax to allow such things like that. Yeah, because it's allowed, like you may know, in Python and many other. But okay. But you could use the input parser class or use one of the methods listed here. Nice way to set function defaults. Using vargin and argin, okay. As we can see, no simple answer, yeah. So we can use input parser class, or we can use one of those methods from here. Uh, okay, input parser class, yeah, standard ways for programming. It always takes a lot of things, yeah. And arg in and arg out, yeah. So, for example, yeah, we can use something like that. So, okay, so there are many ways of doing this. Either we can use something like this kind of the block, yeah. As it's in modern MATLAB supports the arguments block. Arguments block says that, for example, the in is 1, 1. So it means that it's simply a scalar of type double. Must be finite. So must be finite. I think this is those are called validators. So validators, it means that simply there's function must be finite that checks if in is finite, and equal to 0, its default value. Okay. So for example, we can use something like that. Is it clear how it works? Or this is obscure? Because other way is to use an arg in, an arg out, check how many arguments, no, yes, yeah. I think this is a little awkward, but still cleaner, yeah. Uh, so let's try to use it. Are you fine with this? Okay. So first is sys. Sys is one by one. It's struct, and and it cannot have the default value because it just must be provided for us. Yeah. The next one is name, and it's string. It should be non-empty string. Yeah. let's get to help for this. Maybe it will provide the list of some kind of those functions that can tell us, because this function is empty, but we want to have something reverse. Declare function argument validation. Yeah. So argname, dimensions, class, validators, default value. Yeah. Can you see it? Um, and so and so. We will just use that one. You can also use this for output. So we can define what is the output. But okay. Declares input arguments for a function. Yeah. The argument block is optional. Yeah. We have lived without it for a long time. If you include one or more argument blocks, they must appear before the first executable line. Okay, so let's start. MATLAB treats argument block that it's not labeled explicitly with input or outputs as an input block, because we will just mostly deal with inputs. Yeah, we won't bother with outputs maybe. Each argument can have one or more restrictions or a default value as shown in the syntax. Yeah. So it can have any of those or none of those. Yeah. None, I don't know if it makes sense, but yeah, you need to provide arguments. So yeah, whatever works for us. Dimensions can be provided like that one. Colo allows any length in that dimension. Okay. Must match exactly. Okay. Class like double. Okay. Validators. Comma separated list of validations functions. So let's see if we will able to find a validator. Why it doesn't want to show me MATLAB? Okay. Okay, must be non-empty. Okay, there is something like that, because we want to have this and to be provided by the user and be non-empty. Okay, nice. Now, next is initial coordinates. And what is the size of the initial coordinates? We can either put it 3, 1, or we can put it comma 1. Yeah. It's tab double, I suppose. I'm not using this super often. I think this is pretty nice, but I'm not using this super often. So let's see. Test will help us if we make something wrong here. Yeah. Double. Okay, we can use just must be finite and equal to 0, 0, 0 as default. Okay. Okay, let's do not overcomplicate. Let's make it just 3, 1. And now run test again. Still there are some issues. Yeah. Errored. So because it doesn't tell us exactly what is the issue, so let's just make this test by ourselves and see what is the issue here. So this is interesting because when I call it, it just works. Does adding body ground to a new system work? Add body. So maybe I have used it in the wrong way. The programming sometimes can be annoying. Asserts that none of the tests corresponding to results are failed. Okay. So it means that we will not use assert success. We'll just call it different in standard way, and simply we'll make this kind of implicit testing that if creation of this body will fail, the test will be simply errored. Okay, so it means that I hope that this will can be used in that way, because it's often the case, but it seems that according to the functionality, it use case is slightly different. So simply that, and we will write this test that assert, for example, so I wrote simply this test that makes system add one body ground, yeah, and then assert left of sys bodies is equal to 1, and they comment the number of the bodies in the system is correct after adding one body, and then it gives how many bodies are actually in the system. Yeah, okay. So I modified it to work it in that way, and now all tests pass. Okay, so it seems that our function for adding bodies seems to work. Maybe. Any questions? Any issues? Everything works for you the way you expected it to work? Okay, perfect. But now we need more tests. Yeah. For example, here for adding bodies, we should add at least 2 more tests or even more. Yeah. So the next test, yeah, would be to check indices of the added body. Yeah. So we can copy paste this. Test contains many copy pastes, yeah. And then uh, so our body I will skip messages at the moment, yeah. So we are ensuring that after we add body, we can get this body here, of course, and we are trying to ensure that coordinate indices are correct. What else we can ensure? That the name is correct and the coordinate values are correct. Yeah. So we are adding body ground and we want to ensure that that the body name is equal to ground. Yeah. Because we are putting their body to have hope that to not to have hope, and you are expecting that the name is correct. The next text should be the check coordinates of the added body. Uh, the field is called it helps with coding. Yeah. I wonder if this will work. Let's see. Okay. This one is not working because it requires this all function. And now it's working. Any questions to what we are doing here? Why and how? Is it clear? For example, why I use all here and why it's not working without this all? Yeah, without all, it doesn't work simply because of how this part is working. Yeah. So let's say that you write something like that. Yeah. Is it true or not? No, it's three truths. Yeah. So this is how it works. Yeah. So this is kind of the problem that uh, it's not necessarily it's true. Yeah. When we take a look on it, but for the language here, yeah, you provide three numbers on the left, three numbers on the right, yeah, and the behavior is to make it element wise, so it compares each of the elements, yeah. So it gives you three values, yeah, true, 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 because it's true for all the three indices, yeah. And just to make it into one entity, you just have to add all above it. And exactly. Yeah, exactly. So if all are true, then all returns true. And if any of those matches doesn't work, then it returns false. There is also any. Any means that if any of those values is true, then it will return true. So it has different use cases. But here we are expecting all of these indices to be true. Yeah. Okay, we're running out of time, so we'll just write two more tests because now we can write a lot of tests for this function. So here we will provide Q0 around 3, 1, and we'll provide here Q0, and we will expect that this matters. Yeah. So what we provide, it's just like here. Yeah. Okay, and it works. Because it's really easy to make this kind of error that you provide something and it's not working exactly as you want. Yeah. And the last test that we write today, and I think that we have to then go home. If it works, adding more than one body. Simply, yeah. And let us allow to be a little lazy. If it works, we can already check, for example, if the name of this body is correct. Yeah. And we can even check if we haven't overwritten the old name. Okay, all this works. So I add here two bodies, check that there are two bodies and that the second body name is link and the first body name is ground. Just to be kind of the safe side. And yeah, we are also running out of time of today. But okay, at least we can tell that our function for add bodies seems to work and our code works that is shown here. Okay. Any questions? Yeah, so as you can see, tests are quite involving and when you start with this, because we have already written quite few of them. Like where are those tests for those bodies? Test add body. Yeah, we already add quite few of them, and we still haven't checked, for example, indices. Now we should add tests here as well to check if the number of coordinates is appropriate when we add more bodies. But it also means that when we will, for example, then we can already rely on those functions pretty well. Yeah? So we can add here several bodies, and we can be almost sure, yeah, that those bodies are added properly. Then we can use the things that are added here in the later stages. So yeah, from some perspective, it makes it also smoother. Unfortunately, it's more visible when the program grows large. Yeah, so at the start, it takes time to write those tests. But okay. Next time we'll try to, I think to fill all the rest of those. I think so. Yeah, let's see. Line 9. Input arguments block declaration and the function line must contain the same input arguments in the same order. So this is the question, I think, that's answered this question at least partly. So yeah, you have to put it. Most likely, you don't have to put all this. It's enough to put the name there. But because we already get it, we put those. This is some type of constraints that we put here. Yeah, because when it enters, it will check that the system is scalar and the system is struct. So if you put here a number, it will fail. Yeah, so you cannot. Because here we have this add body, and if we put here 1, because why not? Yeah. Invalid argument is position 1. Value must be of type struct or be convertible to struct. Yeah. So it doesn't even try to do anything with it. It already knows that it's incorrect, so it won't work. So yeah. So if you just want to do something like that, yeah, but it seems that this is the feature that you have to provide all of them.
And the system one and one, it's like it's a structure that could be of any dimension, like have many properties in it, but
Yeah.
scale one by one.
Yeah. Dimension is slightly different. Okay, so let's add another body. Link, yeah, with 0, 0. And then you can see the struct is 1, 1. But if you open it, then you have 1, 2 struct, for example, for bodies. So bodies will add, so it will still struct, yeah, because there's one entity with multiple fields. It's treated like just like scalar because it's one structure. Yeah, it has many fields, but structures as a data type just contain fields. Yeah. So yeah. And here you can see that if you have structure 2 by 1 like this bodies, it's simply arranged that way. Yeah, that this is this array of all those fields. But the size only apply to the number of those like rows here. Anything else? Yeah. Okay, so first of all, I have to upload it. And then I will put the link in Moodle. Yeah, but no, just to, if there's this is open in repository and you just want to download it, like zip file or something, that you can do this without any logging. Just you can go to some repository and download it, and that's all. It should work that way. If not, let me know and I will upload this Moodle, but I don't think that they change it because it's commercial system. They could also always change it, but yeah, I'm pretty sure you can just get it. Okay, anything else? If not, yeah, let's hope we see next week and we'll continue from this point. So we will just, yeah, going with adding those features. Okay, thanks. Thank you. Bye.